Welcome back to Linear Systems and Signals, and now we want to turn to calculating the power of a signal for signals which are what we call power type. So basically what we want to do is compute the power of real and complex signals, and we'll do this, in particular we're going to be looking at periodic signals because those are ones for which the power calculation is relatively straightforward. So remember from before that signals can have infinite energy. We saw before that the sinusoids in particular, these cosines and sines, have infinite energy. So we saw this in continuous time. For an example, x of t equals cosine 10 pi t. We see the same phenomenon in discrete time. So if I took a discrete time a cosine, which I can plot, I can plot over here, then you can see when I take the instantaneous power, so this is the instantaneous power, we're going to get the magnitude squared. But now we're adding up these numbers. We're adding up all of these numbers here, and you can see pretty quickly that it's the energy is going to be infinite. So the question is, well, periodic signals are definitely signals we're interested in. So if the energy is not a meaningful calculation, what is a meaningful calculation? And that turns out to be the power, which is the energy per unit time. So the power of a signal is the average energy per unit time. So if I give you a signal x of t, you first calculate the instantaneous power, then you integrate it over some time period. So for example, we can start integrating it from, say, -2 to 2. If we integrate from -2 to 2, then what are we doing? We're kind of calculating the the area under this x of t squared, and then we're going to divide by this factor 1 over 2t, which is the length of this interval. So we're looking at the instantaneous, they're adding up all the instantaneous power, so we're essentially computing the energy from minus t to t. Right, so this is the energy from minus t to t. And then we're dividing by 2t, so we're going to get the average energy, which is power, energy over time. And then what we're going to do is we're going to expand our window. We're going to look at, as t gets bigger and bigger, we're looking at longer and longer chunks of the signal, and we're asking, okay, what's the total energy in there? And let's divide by the total time. And hopefully that converges to something. And if it converges to something, it's going to converge to the power of the signal. So if I take the magnitude squared of this signal, I would get this. And so what is it? So just pictorially again, what are we doing? Well, we're going to be integrating. We're going to be integrating the area under the curve. So we can start out here, and then we can move farther and integrate out over longer and longer chunks. And as we expand out, we can see we're going to be integrating more and more. So let's take a look at that as we go. So here again, I'm plotting the instantaneous power, and we're calculating the area underneath the curve. That's what the integral is, the area underneath the curve of the instantaneous power. And so here I've set capital T to look at three humps here, and I take the total area under those 3 humps of the instantaneous power, and then I divide by the width of those 3 humps, and that's going to give me the power. And you can see here that this thing is going to, if we keep going, we can do 5 humps and then divide by 5, but it still ends up being like the energy, so the total energy in one hump divided by the width of that hump is what we're going to get. As we go in the limit with these periodic signals, we're just adding up the same thing over and over and over again and dividing by a bigger number, but that bigger number is growing at the same rate as the area under the curve. We can do the same thing in discrete time. So in discrete time, the power of a signal is defined in the same way. Here we're looking at again, this is the number of points. Number of points. So this is the number of time points between minus n and n. And like the issue here is, of course, that time 0, you have to count that one in as well. So you get n negative ones, n positive ones, and capital N negative ones, capital N positive ones, and one more for 0. So that's why you get 2n minus 1. And we're again calculating we're calculating the instantaneous power. Instantaneous power. We're adding it up to get this total thing is the energy in minus n to n. And then we're dividing by the length of that interval. So that's what we're computing for average power, and we look at wider and wider intervals. So if we take a look at that, we again take the instantaneous power, and then we're just going to be again adding up, expanding a window and adding up, the total height of all those lollipops now that are these stem plots that are under the contribute to this instantaneous power. So first off, we start, say, if we take n equals 4, we're adding up the first 4 and the last 4, from negative 4 to 4. So we're going to divide by 9, but then we might look at negative 8 to 8 and divide by 8 plus 8 is 16 plus 1 is 17. So that's 2n plus 1 is 17, and so on and so forth. We can keep expanding out. So this suggests that for periodic signals, we should be able to come up with a simpler formula. And that simpler formula is actually pretty straightforward. It's the and we can derive it relatively easily. So if I want to look at the average power, the power of a signal, I can look in an interval from minus t to capital T, but I'm going to choose particular values to look at for minus t and capital T. In particular, I'm going to look at the period t naught, and I'm going to look at integer multiples of t naught. So that's what I get here. I'm going to say I'm going to take kt naught to minus kt naught, and so I'm going to be dividing by the total length of that interval, which is 2kt naught, right? And here again, I'm integrating the instantaneous power, and since I've converted everything into k's, I'm now taking, instead of taking this limit as t goes to infinity, I'm taking the limit as k goes to infinity. So that's adding up those humps. Basically, I'm adding up one hump at a time as I go, expanding outwards, and I'm dividing by the total area of each of those humps. If I look, so now what we can say is that this is the, this thing here, this thing here is the total energy, in 2k periods of the signal. Right? And so what that is this is the total energy in one period. Right? So that's why you get this 2k factor here. And then, of course, this 2k is going to cancel that 2k. And then we're just left with this t naught and the integral over one period. So this is the average energy over one period. That's what the power is. The power of periodic signal is the average energy over one period. If we want to do an example, we can look at a complex periodic exponential. And it's a good example of power type signal. So let's just look at the simplest case. So we take x of t is equal to e to the j omega naught t. And then we're looking at the average energy in a single period. So we're taking the length of the period, 1 over t naught. So t naught is going to be, t naught is equal to 2 pi over omega naught. And we're going to integrate over this interval from 0 to t naught. And then we're going to divide by the same t naught, right? But now we can look here, we have this, we're going to be taking the magnitude squared of this complex exponential, but the magnitude squared of e to the j something is just going to be 1. So that's why we get this integral here turns into this thing is equal to 1. So that's why we get this 1 here, and then we're just integrating 1 from 0 to t naught, and then divided by t naught. So we're going to get a total power of 1. It's also important to notice here that we can write this as the real part of e to the j omega naught t squared. We can take the real part plus the imaginary part. That's the magnitude squared. Right? And here, the real part of e to the j omega naught t, this is going to be cosine omega naught t squared, and this imaginary part is sine squared omega naught t. Right, so because we're using the decomposition, e to the j omega naught t is equal to cosine omega naught t plus j sine omega naught t. So if we wanted to look at just the power of the cosine part, if we look at that instead, so we're looking at this cosine part, we can go through the same exercise. We take the total the average energy in a single period. So here we're going to take the square of the cosine. That's the energy in the cosine, instantaneous power in the cosine, and then we're going to integrate over one period. And then we can use our trigonometry formulas to convert this cosine squared into a double cosine 2 omega naught theta. And then when you do this integral, you're going to get that in the end, your power is a half. So the question is why? And the answer is that this is half the power of e to the j omega naught t. Right, now that's the sine term. If you should redo this calculation with sine squared. You should also get a half because the other half of the power is in the imaginary part. So we're saying here that this thing is actually going to be equal to a half, and that this thing is also going to equal a half. So that's what's I mean this whole term rather is going to equal a half, right? Contribute one half to the total total power. Okay. So we can do the same thing with a discrete time signal. So if we have a periodic discrete time signal, we can look at, it's a little bit messier, but we can look at integer multiples of n naught if the period is n naught. So period n naught, we can look at integer multiples of n naught. So we're going to look at kn naught minus kn naught, and so we're going to get that 2 kn naught, and then we have that plus 1 because of x of 0. Then you can basically do the same calculation. It gets a little bit messier, but what happens here is this x of 0 term is going to eventually go away. That's the upshot of this story, is that it goes away. So we're going to get this nice formula, which is that the instantaneous power is again the average average instantaneous power over one period, right? And here again, one period is n naught long, so we take any n naught chunk, length n naught chunk of the signal xn, and then we take the total energy in there and we divide by the length of that that single period. So that's an example. Those are the examples of power calculations, and in the you can practice some other signals you want, maybe some sums of cosines and sines, to try and give yourself a feel for how these power calculations work.